Hello, today we're going to review the Chapter 1, Section 4 exercises. The first few problems are just fill in the blank, short answer. Number 1, the thermal energy in an object is the total of all the kinetic energy associated with the motion of all the atoms and molecules that make up the object. Number 2, the temperature of an object is determined by the average kinetic energy associated with the motion of all the atoms and molecules that make up the object. Number 3. A thermometer marked with a Celsius scale is placed in an ice-water mixture and allowed to reach thermal equilibrium with the mixture. The temperature indicated by the thermometer is 0 degrees Celsius. Number 4. The thermometer from exercise 3 is placed in a pan of boiling water and allowed to reach thermal equilibrium. The temperature indicated by the thermometer is 100 degrees Celsius. Number 5 says a television news report includes an item about a medical care crisis in Sao Paulo, Brazil. Due to the period of very hot weather, Sao Paulo has 12 consecutive days with temperatures above 41 degrees Celsius. What is the temperature in degrees Fahrenheit? So for this problem, we need to use the equation. The temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. Substituting in our temperature in Celsius, we will get 9/5 times 41 plus 32. Typing this into your calculator, you will get an answer of 105.8 degrees Fahrenheit. Number 6. A severe weather warning for the area near Bettles, Alaska warns that the low temperature tonight is expected to reach negative 45 degrees Fahrenheit. What is the temperature on the Celsius scale? For this one, we are going to use temperature in Celsius is equal to 5/9 times the quantity of the temperature in Fahrenheit minus 32. We make our substitution and we get 5/9 times the quantity of negative 45 degrees Fahrenheit minus 32. Enter the numbers into our calculator and we get an answer of negative 42.8 degrees Celsius. Number 7. A heat pump air conditioning unit has a heat exchanger coil on the outside of a house. On a summer day, the gas flowing through the coil has a temperature of 145 degrees Fahrenheit when the outside air temperature is 95 degrees Fahrenheit. Will heat flow into or out of the gas in the heat exchanger coil? Explain your answer. Because heat always flows from high temperature to low temperature, the heat will flow from the 145 degree Fahrenheit coil into the outside air temperature of 95 degrees Fahrenheit. Number 8. On a winter day, the gas flowing through the heat exchanger coil in exercise 7 has a temperature of 20 degrees Fahrenheit. When the air temperature is 35 degrees Fahrenheit, will the heat flow into or out of the gas in the heat exchanger coil? Explain your answer. Again, heat always travels from high temperature to low temperature, so heat is going to flow from the 35 degree Fahrenheit air into the 20 degree Fahrenheit gas in the heat exchanger. Number 9 says the temperature of an ice cube is 0 degrees Celsius. The temperature of liquid oxygen in a container is negative 183 degrees Celsius. The ice cube is placed in the liquid oxygen. Will heat flow into or out of the ice cube? Again, heat flows from high temperature to low temperature, so it is going to flow from the ice cube that is at 0 degrees Celsius and into the liquid oxygen at negative 183 degrees Celsius. Number 10. Suppose you could measure very accurately the temperature of water at the top and bottom of a waterfall. Would you expect the temperature to be different? Explain your answer. This one requires some critical thinking skills. You need to recall that temperature is defined as the average kinetic energy of a body. When water is flowing over a waterfall, it has less kinetic energy at the top of the waterfall than it has at the bottom. So if the water molecule's kinetic energy is increased by falling and getting faster and faster as they fall, you would expect the temperature at the bottom of the waterfall to be slightly more than the temperature at the top of the waterfall because of the added kinetic energy. Number 11. When wax melts, is heat absorbed or released by the wax? In order for something to melt, in order for a solid to melt, it has to have heat added to it. During the transition, it continues to absorb heat. When wax freezes, is heat absorbed or released by the wax? This is the opposite of number 11. So when a body is becoming solidified, it is releasing heat to give up some of that thermal energy. So in number 12, the wax is releasing heat into its environment. Number 13, explain the difference between thermal energy and heat. Thermal energy is a measure of the total kinetic energy that all particles of an object possess. Heat is how much energy flows from one object to another object because of a temperature difference. Explain the difference between temperature and heat for number 14. Very similar to the difference between thermal energy and heat, except temperature is the average kinetic energy of all the particles of an object, whereas heat, again, is how much energy flows from one object to another due to temperature differences. Number 15. When you place an ice cube in a glass of warm water, what happens to the temperature of water in the glass? Use the definitions of heat and temperature to explain why this happens. When you place the ice cube in the glass, the ice cube begins to absorb heat from the warm water and starts to melt. If there is enough ice and little enough water, the water in glass will reach 0 degrees Celsius, in which case the temperature will maintain until the ice is completely melted. Otherwise, the ice cube will melt completely at a temperature greater than 0 degrees Celsius. Number 16. A thermometer at room temperature is placed in a glass of cold water. After the thermometer and water come to thermal equilibrium, how do their temperatures compare? They're the same. Does heat flow into the thermometer or out of the thermometer? Because the thermometer is at room temperature and the glass of water is cold, heat flows out of the thermometer and into the water. Does heat flow into the water or out of the water? Well, I just answered that. Number 17. Suppose the glass from exercise 16 contains only a few drops of cold water. Why is it impossible to accurately measure the initial temperature of the water with the thermometer? Well, this is going to be because the instant that you put the thermometer in the water, heat begins to transfer. And so the temperature that the thermometer is reading will start to go down. However, it probably isn't going to reach the initial temperature that the water started at by the time it comes to thermal equilibrium. Number 18. The energy value of food is determined by burning a sample of the food and measuring the heat released. The energy rating assigned to the food is actually a kilocalorie, which is 1,000 calories, written as calorie with a capital C. Thus, 1 kilocalorie is equal to 1 calorie with a capital C, which is equal to 1,000 calories with a lowercase c. Part A of this problem says the nutrition facts for a popular brand of cookie are shown to the right. How many calories are in one of these cookies? Well, food labels are given by serving size. So this particular label says that the serving size of cookies is 3 cookies. So there are 3 cookies per serving. And in one serving, there are 160 calories with a capital C. If we divide 160 calories with a capital C by 3, we will get that there are 53.3 calories with a capital C, or kilocalories, in one cookie. How many calories of heat would be released from burning one of the cookies? Well, I feel that this C is a misprint and it should probably be a lowercase c, because we just figured the answer to this problem out in part A. So I'm going to say 53.3 kilocalories times 1,000 calories per kilocalorie is going to be 5,333 calories of heat are released from burning one cookie. Number 19. A car's engine block is made of iron and has a mass of 210 kilograms. How much heat is absorbed by the engine block when its temperature is raised from 20 degrees Celsius to 90 degrees Celsius? For this problem, we need to use the equation that heat is equal to mass times specific heat, in this case the specific heat of iron, times the change in temperature. I'm going to need to look up the specific heat of iron in table 1.7 on page 71 in your book. And the specific heat of iron is 0.16 kilocalories per kilogram degrees Celsius. We know that the mass of the iron is 210 kilograms. I just told you what the specific heat was. 0.16 kilocalories per kilogram degrees Celsius. And the change in temperature is the final temperature, 90 degrees Celsius, minus the initial temperature of 20 degrees Celsius. Typing these into your calculator and getting an answer gives you 2,352 calories of heat. Number 20 says you're measuring the specific heat of tungsten. You heat a 215 gram sample of the metal to 100 degrees Celsius and place the sample in 450 grams of water at 20 degrees Celsius. The tungsten and water reach an equilibrium temperature of 21.5 degrees Celsius. What is the specific heat of the tungsten? So to solve this problem, we have to work backwards. We have to figure how much heat the water gains due to the hot tungsten being placed in it. And we're going to use the same equation we did above, mass, in this case of water, times the specific heat of water, times the temperature change of the water. We know that the mass of the water is 450 grams. We're going to multiply that by the specific heat of the water, which conveniently is 1 calorie per gram degrees Celsius. We're then going to multiply that by the change in temperature of the water, and we know that the final temperature of the water was 21.5 degrees Celsius minus the initial temperature of the water, which was 20 degrees Celsius. Calculating that gives us 675 calories of heat transferred from the tungsten to the water. Now we need to use the same equation to solve for the specific heat of tungsten. So because the heat that the water gained is equal to the heat that the tungsten lost, we are able to do that. So we'll have the heat that the water gained is equal to the mass of the tungsten, which the symbol for tungsten is W, times the specific heat for tungsten, which is what we want to solve for, times the change in temperature of the tungsten. Algebraically solving this, we get that the specific heat of tungsten is equal to the heat that the water gained divided by the mass of the tungsten times the change in temperature of the tungsten. Substituting our values in, the heat that the tungsten lost is equal to 675 calories divided by the mass of the tungsten, which is 215 grams, times the change in temperature of the tungsten, which is its final temperature of 21.5 degrees Celsius minus its initial temperature of 100 degrees Celsius. When we calculate this out, we are going to get a negative 0.04 calories per gram degrees Celsius. However, it's specific heat, so it is going to be a positive number, and it's going to be 0.04 calories per gram degrees Celsius. For the last problem, number 21, a 25-gram sample of ice has a temperature of negative 10 degrees Celsius. How much heat is needed to convert the ice into steam? So this problem is very similar to example 1.17 in your book, except it adds an extra part at the end. So we need to deal with 4 different sections of this problem and find the heat involved with each one. We have to go from negative 10 degrees Celsius to 0 degrees Celsius. Then we have to talk about the ice cube melting. Then, give me a little bit more space for that. Then we have to talk about going from 0 degrees Celsius to 100 degrees Celsius. Finally, we need to talk about the water turning into steam, which is evaporating. For the first part, we're going to use heat is equal to mass times specific heat times change in temperature. So the mass of this sample is 25 grams times the specific heat of ice, which again is found in that table 1.7 and is equal to 0.49 calories per gram degrees Celsius, times the change in temperature of the water, which is 0 minus negative 10 degrees Celsius. Yes, I know, I ran out of room here. Calculating this, we get that there are 122.5 calories of heat involved in changing the temperature of this ice by 10 degrees. To figure out the energy involved in melting this ice, we need to use the equation heat is equal to the mass of the sample times the heat of fusion of the material. The heat of fusion for water and ice is 79.8 calories per gram. The mass of the sample is 25 grams, so we simply multiply those together. And when we do that, we get 1,995 calories. To change the sample from 0 degrees Celsius to 100 degrees Celsius, we are back using the specific heat equation. The mass of the sample is again 25 grams. We know the specific heat of water by this point is 1 calorie per gram degrees Celsius. And we are changing from 0 to 100 degrees Celsius. So that is going to be 100 degrees Celsius minus 0, which is just 100 degrees Celsius. Multiplying these together, you get 2,500 calories of heat to change it to 100 degrees Celsius. Finally, to figure out the heat for this sample to change to steam, we need to use the equation heat is equal to mass times the heat of vaporization. This value is found in table 1.8 on page 75. I should have mentioned that before. It's the same place the heat of fusion was found. And for water, the heat of vaporization is equal to 540 calories per gram, multiplied by our sample size of 25 grams, gives us 13,500 calories of heat. Lastly, we want to add those all together to get our total heat. So we have 122.5 calories plus 1,995 calories plus 2,500 calories plus 13,500 calories. And when we add those together, we get 18,117.5 calories in order to change a 25-gram sample of ice to steam.